All right. Welcome to class. So today we're going to start our new chapter, still about multiple regression analysis, but this time we focus on inference, okay? Chapter 2 taught us how to estimate beta hat, right? And how to check if OLS is unbiased and efficient. That was all about getting the best possible number from our sample. But here is the problem. Our sample is just one sample. If we took a different group of people, we'd get a slightly different beta hat. Think about all of you guys, okay? You started with the same question, but different of you collected different data. So each of you gonna have a different beta hat because of different sample. So a natural question is, can we trust this number? Can we trust your estimation? Is it really different from 0, or could it just be random noise from this particular sample? That's exactly what inference means, okay? Using our sample estimate to make a broader statement about the true population value. Okay, two main tools do this job. First one, we need hypothesis testing. We need hypothesis testing, asking, is this effect really there, or could it just be 0? Next one, we need confidence intervals. So confidence interval means giving a range of plausible values for the true beta instead of just one number, okay? So confidence interval gonna give you a range of our estimate about the true beta. To do either of this, hypothesis testing or confidence interval, we need one more assumption beyond MLR1 to MLR5. Still remember the assumption for multiple regression? So here we need one more assumption, all right? You see, in economics, we have assumptions, but even more in econometrics, we have more assumptions, right? So this assumption about the shape of the error terms distribution, that's where we'll start today. This slide previews the whole chapter, okay? Let's walk through the logic step by step. Statistical inference has two goals, okay? Run hypothesis test about the true population, beta, and build confidence intervals around it. Sampling distributions of the OLS estimates, okay? Here is the key idea. Beta j hat is not just one fixed number, okay? Remember, our OLS estimator, suppose it's beta j hat. This beta j hat is not one fixed number, okay? Different people, different sample can have different beta j hat. Every time you draw a new sample, you get a slightly different beta j hat. So beta j hat is actually a random variable. It has its own distribution. You learned it from statistics, right? As long as x is a random variable, it has its own distribution across many possible samples. From chapter 2, we already know two things about this distribution. Its expected value, okay, which means expected value of beta j hat equal the true. This means unbiasedness, okay? And its variance, okay? The precision formula we derive. What is the formula? Still remember? Sigma square hat times x transpose x inverse, okay? Those two, one is about expected value, another one is about variance. This is what statistic cares about, all right? But for hypothesis testing, knowing just the mean and variance, this is the mean, this is the variance, isn't enough. We need to know the exact shape of the distribution. Is it bell-shaped, skewed, or something else? Then can we calculate probabilities like how likely is it to see a beta hat this large by pure chance? So we need to know the exact shape of the distribution, okay? So here, in order to derive the assumption distribution, we need additional assumptions. This assumption is about the distribution of the errors, which is normal distribution. You will hear this one often, okay, in statistics and econometrics. This is the missing piece that lets us go from just knowing the mean and variance to actually testing hypothesis, okay? Here is the new assumption, MLR.6, which is normality, okay? Normality of the error terms. In plain words, it means the error term follows a bell shape, centered at 0 with constant variance, sigma square, and this bell shape doesn't change no matter what the x values are, okay, which is independently of xi1, xi2, all the way through to xik. Look at the 3D picture at every value, okay, at x1, x2, x3, the error terms form the same little bell-shaped curve, okay, just shifted up or down along the regression line, okay? Remember, this is our regression line. How we call this regression line? Population regression function, right? Population regression function, which is expected y given x equal beta 0 plus beta 1x. This is the true one. The shape and spread of the bell stays identical, right? Identical everywhere. Only its location shifts along the line. This is really MLR5, constant variance, plus a specific shape, which is normal distribution combined together, right? Why does this matter? Because now we get a bonus result showing at the bottom. If, okay, so here, if mu is normal, then y itself is normal too. Conditional on x, of course. Conditional on x, y is normal distributed with the mean, which is beta 0 plus beta 1 x1 plus all the way through to beta k xk. This is the mean, okay? And then with the constant variance, sigma square. VAR means variance. Why do we even believe mu is normal? Let's discuss where this assumption comes from and its limits. Okay, the argument is that the mu is really the sum of many small unobserved factors, right? We didn't include in our model. And there's a famous statistical result, which is Central Limit Theorem, okay? CLT, which means Central Limit Theorem. It says that if you add up many independent factors, the sum tends to look normal, regardless of what each individual factor looks like. So the hope is that mu, being a sum of many things, ends up approximately bell-shaped. But three real problems with this argument. The first one, how many different factors number large enough? Okay, so central limit theorem works better with more factors, but we don't actually know how many are hiding in mu, okay? Or if there are enough for the approximation to kick in. So this is the first problem. The second one, are those factors similar enough? Which means heterogeneous here, okay? Heterogeneous here. Or how you pronounce this one? Heterogeneous, okay, thank you. Possibly very heterogeneous distribution of individual factors. This means central limit theorem assumes the individual pieces aren't widely different from each other in behavior, but real unobserved factors could be very different in nature and size. Next one, how independent are the different factors? So the question is that, are they actually independent? Central limit theorem needs the factors to be roughly independent of each other, but real-world unobserved factors are often correlated with each other too, right? So this is the challenge and problems. Okay, so here, that's why the normality of the error term is an empirical question. Okay, it's an empirical question. At least the error distribution should be close to normal, okay, close to normal. In many cases, normality is questionable or impossible by definition. So that's why when I'm not sure, have you started to your literature review about your economic paper? So in the published paper, you will see that the researcher, they assume that the error term is normal distributed, okay? So we assume in advance. We didn't prove that because it's very hard to prove. But thanks to the central limit theorem, okay, normality, okay, the distribution is close to normal, okay? So this is the key point. Let's look at examples where normality clearly fails. Examples where normality can't hold. Think about the wages, okay? The data, it's non-negative. Also, we have minimum wages, okay? Minimum wage, which means wage cannot be normal. A normal curve stretches to negative infinity, but wages can't. Next one, number of arrests. Because the number of arrests only takes small integer values, 0, 1, 2, 3, right? Normal is continuous and smooth. You remember the normal distribution? Bell-shaped, right? This is the mean, and this is the variance, okay? So for number of arrests, it's discrete integer. And also unemployment, because it's an indicator value, right? Takes only 1 or 0, about as far from the bell-shaped as possible. This is binary, okay? But the good news is that sometimes we can fix this with the transformation. How do we do that? You saw the paper. How do they do the data transformation in order to get the normal distribution? Take the natural log, right? Take the natural log of the variable. So you see, we use log wage instead of wage itself. This is why you see log wage everywhere in this course. Why do we care? Because if mu is normal, OLS is the blue, right? Best unbiased linear estimator, even better than nonlinear alternatives. Most important point on this slide, for inference, okay, t-tests, confidence intervals, we don't need normality if the sample is large. If we have large sample size, we don't care about normality. With a large sample, central limit theorem kicks in a different way, and our test statistics become approximately normal anyway. Be careful here what I said, approximately normal, okay? I didn't say exactly normal. This is why your advisor always suggests you get more data, right? Because of large sample size. So the rule of thumb is that if you got a small sample, depends on your topic, okay? If you got a small sample, normality matters. But if you have a large sample, don't worry about it, okay? Don't worry about the normality. Or you may want to research about the e-commerce. Can you get a large sample for e-commerce? If you get the data like the monthly data or daily data, like the stock price, of course, you can get as many as possible, right? How about the annual data, which is yearly, year by year? For e-commerce, maybe the maximum you can get is about 20 years, right? So basically, we don't see its large sample, okay? So be careful about your sample size. Next question is, we are talking about the large, but how large is large enough? Any idea how large is large enough to say that I don't need to care about the normality? Any idea? We don't have any law or theory to say this, okay? But a common rule of thumb, okay, is if your N, your observation is greater than 30 for sample cases with well-behaved error. Okay, If your sample is about 30, you cannot put 30x into your model, okay? It will confuse your estimate, your model. And here, you need well-behaved errors. What does it mean? What do you mean by well-behaved? So you need to check your error term, okay? It should be centered around each other, not like messy up, okay? Not messy up. This is from the textbook, okay? We need well-behaved errors, but actually, error term is unobservable. We don't know what it looks like. This is just in textbook how we say that, okay? How we define that. Next one, if your n is greater than 100, or more when errors are heavily skewed, or the arrow have a fat tail, think about in finance, okay? In finance, the error term of the financial data, basically it's not normal distributed. It's somewhere skewed, but not sure about left skew or right skew, but they are not normal distributed, all right? So if you are doing about finance, be careful about using the normal distribution assumption, okay? Because basically, when you present your work, the advisor will question you, okay? Question about your error distribution. So there is no universal magic number, okay? It depends on how non-normal your errors are. There's no magic number. The bottom line is that for our new assumption, this one, normality is a small sample crunch, okay? It's for small sample. In large samples, okay, in large sample, the central limit theorem automatically gives beta j hat an approximately normal distribution regardless of what the errors look like. So all your t-tests and f-tests remain valid asymptotic, okay, asymptotic. We're gonna talk about testing later. This is why in most applied economics, you will see it with large data sets. Researchers don't worry much about whether errors are exactly normal because the sample size takes care of it, okay? Clear about this? One more assumption. Okay, let's move on. Let's recall the terminology, all right? So from MLR1 through MLR5, together we call Gauss-Markov assumptions, okay? Gauss-Markov assumptions. And if we add MLR6, which is normality, and now you have the classical linear model assumptions, in short term, CLM assumptions, okay? Now, why do we add normality? Because it gives us a very powerful result, which is theorem 4.1. Under assumptions 1 through 6, each estimator beta j hat is normally distributed around the true beta j with the variance we already derived in chapter 2, okay? This just says our estimator is a random variable and its sampling distribution is a normal bell curve centered at the true value. Second formula, standardize it. So we subtract the mean divided by the standard deviation, and you get a standard normal, which means the mean is 0 and variance equal 1. I remember in your statistics, right, you need to transform the normal distribution to standardized normal distribution, okay? So this is the standardized normal distribution. Why do we care about this? Because this is exactly what lets us build t-tests and confidence intervals, the tools we'll use for the rest of this chapter. Without normality, we don't get this clean result in small samples, okay? So I emphasized a lot, normality is very crucial for small samples, all right? Last slide, we use standard deviation, which is beta j hat, which is the true standard deviation. Be careful about the terminology, okay? Standard deviation, actually, this is the true. This is the true standard deviation. The problem is the same. We never actually know the true one, okay? Because it depends on the unknown error variance. So in practice, we estimate it and we call it standard errors. So you see here the difference. One is standard deviation, another one is standard errors. Standard errors always mean the one that we estimated, okay? This is the estimated. We have new theorem 4.2 says that once you replace SD with SE, the estimated version, the distribution changes. It's no longer exactly normal. It becomes t-distribution with n minus k minus 1 degrees of freedom, okay? N is the sample size. K is the number of independent variables. What does 1 mean? One means the degree of freedom for the intercept, right? So basically, because remember multiple regression, y equal beta 0 plus beta 1 x1 plus beta 2 x2 plus all the way through to beta k xk plus mu, okay, don't forget. So basically, k is the number of independent variables, okay? So 1 means the intercept, which is beta 0. That's why degree of freedom is n minus k minus 1. Why the change? Why? Because now we have extra estimation uncertainty from estimating the standard deviation itself, and the distribution accounts for that. Okay, here's the note. The t-distribution is close to the standard normal distribution if n minus k minus 1 is large. So in large samples, it barely matters. T and normal gives almost the same answer. Now, hypothesis testing, the most common null hypothesis, which is H0 means null hypothesis. Because we want to test that, is it beta j different from 0? Okay. What does this mean economically? It says that holding other x fixed, xj has no effect on y, right? If beta j equals 0, which means xj doesn't affect y. This is the hypothesis we test most often. Does this variable actually matter once we control for everything else? If beta j equals 0, which means H0, our null hypothesis, is true, right? Next one, now we build the actual test statistics, the t-statistic or t-ratio, all right? What is the formula? T beta j hat divided equals beta j hat divided by the standard error of beta j hat, okay? Just the estimated coefficient over its standard errors, okay? So the t-statistic will be used to test the above null hypothesis, which is here. This is our null hypothesis. The farther the estimated coefficient is away from 0, the less likely it is that the null hypothesis holds true. But what does far away from 0 mean? What does it mean here? If beta hat j is far from 0, that's the evidence against our null hypothesis, okay? But far compared to what? We need a scale. That scale is the standard error, the variability of our estimate. So the t-statistic literally answers how many standard deviations is our estimate away from 0. If you have a big T, estimate in many standard errors from 0. If you have a bigger T, which means you have a strong evidence against H0. If you have a small t, estimate is close to 0 relative to its own noise, okay? So this is weak evidence against H0. Let me write it down. If you have big T statistics, okay, so strong evidence against H0. But if you have a smaller T, so you have weak evidence. Now look at the distribution. Look at the distribution of the t-statistic if the null hypothesis is true. Okay, if H0 is true, meaning beta j really is 0, right? Then this t-statistics simplifies to beta j hat divided by standard error of beta j, which by theorem 4.2 here follows a t distribution when with n minus k minus 1 degrees of freedom. So Here is the goal. We want a rejection rule. We pick a cutoff so that if H0 is true, okay, if H0 were actually true, we'd only reject it a small percentage of the time. Usually 5%, okay? This 5% is called the significance level. Next slide will show exactly how we see that cutoff, okay? So let's visualize it. Now let's actually build a rejection rule, all right? And here is one-sided test. Remember our null hypothesis, which is H0, is beta j equals 0 against beta j is greater than 0. This is the directional hypothesis. We simplify expect a positive effect based on economic theory. Since we expect that beta j greater than 0, so we reject H0 only when beta j hat, and therefore the t-statistic is too large, okay? Or, which means the t-ratio is too far in the positive direction, not too negative, just too positive. That's why the shaded rejection region is only the right side of the curve, okay? Take a look at here. The shaded area, we call it rejection region, okay? And how large is too large? We pick a critical value so that if H0 were true, we'd only landed in that rejection 5% of the time. That's the shaded area, okay? 5%, which means 0.05 in the picture, okay? 0.05, this means 5%. In this example, okay? In this example, with 28 degrees of freedom, the critical value is 1.701, which is here, okay? This is our critical value. This number comes straight from the t-table, right? So it's from the t-table. I think you can find your t-table from your statistics. So the decision rule is that if your t-statistic is greater than 1.701, we reject H0. Otherwise, we fail to reject. Be careful here. We didn't say that we accept H1, but we say that we cannot reject H0, okay? It doesn't mean we accept H1. It means we cannot reject H0. One thing to notice, this is only one side, okay? If beta j hat come out very negative, it should be the other side, okay? We would not reject, even though it's far from 0, because a one-sided test in this direction only cares about large positive deviation. So here, let's apply this to a real example, a wage equation. Have you run the wage equation in the first lab? Wage and education. So basically, the question is that after controlling for education and tenure, higher work experience leads to higher hourly wage or not? Be careful, we need ceteris paribus, okay, here. Here is the estimated equation. Log wage hat equal intercept plus 0.092 education, okay, plus 0.0041 experience plus 0.022 tenure. Below each coefficient in parentheses is its standard error. That's what we divided by to get the t-statistic. Be careful here, guys, because when you report your estimation result, you should follow this format, okay? Your coefficient above, and then below it, it's your standard error of that coefficient, okay? But normally we use parentheses. It's the standard error. Okay, so n is observation. This is our R squared. And here we're going to focus on experience. Its coefficient is 0.0041. Standard error is 0.0017. Can you calculate the t-statistic of experience, please? How we calculate? How we calculate the t-statistic? You guys woke up? So here, our H0, which is null hypothesis, beta experience equals 0 against alternative hypothesis, which is H1. Beta experience is greater than 0, okay? One would either expect a positive effect of experience on hourly wage or no effect at all. So we need to test those hypotheses, okay? Next one, how we calculate the T ratio of experience? Expected, the estimated coefficient divided by its standard error, right? So you got approximately 2.41. This is the T ratio. What is the degree of freedom? N minus K minus 1, which is 522. K equal 3, right? Because we have 3 axes, okay? Education, experience, and tenure. That's why K equal 3. Look at the degree of freedom. Here, the standard normal approximation applies because 522, which is a large sample size, all right? So with this large, the t distribution is essentially identical to the standard normal. That's why we can just use normal critical values here. Okay, so let me write it down. With this large, t distribution is identical to the standard normal. Here are two conventional critical values, okay? Which means this is the traditional critical value that we use. The first one, 1.645 for 5% significance level and 2.326 for 1% significance level, okay? Our t statistic, which is 2.41, compare 2.41, which is greater than 1.645 and also greater than 2.326, right? Which means we can reject our null hypothesis at 5% or even at 1% significance level. So basically, 1% is more stricter, okay? It's stricter. Because our t ratio is 2.41, greater than 2.3, to 6, the critical value at 1%. So basically, we can reject our H0. That means beta experience is greater than 1, not equal to 1, okay? So how we explain? In plain economic language is that the effect of experience in terms of the original question, not just reject H0 here. More experience rarely is associated with higher wages, holding education and tenure fixed, okay? Or here, the effect of experience on hourly wage is statistically greater than 0 at the 5% and even at the 1% significance level. Okay, let's see the graph. I think it's better. $2.41. Okay, let's go back to this one because we need positive here. Basically, this is our critical value. 2.41 is somewhere here. You see, our T ratio is in the rejection region. That's why we can reject H0. So this is a positive side. Let's see the negative side, okay? But here, one-sided alternative, which is less than 0. So here, we want to test H0, beta j equals 0 against H1. Beta j is less than 0. You see, less than 0. That's why we use the left side of the distribution. Here we expect a negative effect, okay? So we reject H0 only when the t-statistic is too large or too small. If we want to reject H0, we expect that the t-statistic is too small or too large. Yes, too small to fall in the rejection region, okay? That's why the rejection region is now on the left side of the curve. Same logic as before, we need to pick the critical value so that if H0 is true, we only reject 5% of the time with 18 degrees of freedom. And the critical value is negative 1.734. Notice that the symmetry with the earlier slide, okay? Same idea, we just flipped around because our alternative hypothesis points to the other direction. The sign of H1 always tells you which tail to look at. Okay, another example, this time testing a negative effect, all right? So we want to test whether small school size leads to better student performance. We have our Y here, right? Percentage of students passing math test. This is the intercept. This is the average annual teacher compensation. This is the staff per 1,000 students. And here is the student enrollment, which is the school size. Now we are caring about the school size, okay? That's why you need to take a look at the estimation coefficient and the standard errors, okay? And here is 408. This is our R squared. This is our hypothesis. Remember, when you write your paper, you need to have your own hypothesis, okay? Which one is your H0? Which one is your alternative hypothesis, H1? So here we want to know that beta enroll is less than 0 or not. So basically, we are asking, do larger schools hammer student performance, or is there no such effect? And then as usual, we calculate the t ratio, right? You use the estimated coefficient divided by the standard error. Okay, this is the coefficient. And this one is the standard error. So our t ratio is negative 0.91. It's too small. In this case, you see, in this case, even we have a high degree of freedom, right? But see our critical value. Can we reject H0? Negative 0.91. Basically, it's somewhere here. Maybe here, right? Negative 0.91 is our t ratio. And you see, it's not in the rejection region. That's why, in this case, we cannot reject our null hypothesis. Okay, first, we cannot reject it at 5%, okay? Even we cannot reject it at the 15%. Basically, we don't use 15%. The percentage that we use is 1%, 5%, or 10%. Basically, you can see that we use the 15%, but here just give you some intuition that we even cannot reject H0 at the 15% significance level. So here, one cannot reject the hypothesis that there is no effect of school size on student performance, not even at a lax significance level of 15%. Let's finish this log version. Be careful, we have log for our x, right? And see something interesting. So you should be familiar with this one. This is our estimation result. You get it from our programming, okay, with the observation and r squared. So here, we want to know that beta log n rho equals 0 is our null hypothesis, or beta log n rho is less than 1, which is our alternative hypothesis. So you need to look at here, right? Can you calculate the t ratio for log n rho? Please calculate. What is the t log n rho? Here, you use which one divided by which one? Be careful about the sign, okay? And then you tell me what is your t ratio here. You get it? The t ratio. You use the estimation coefficient, negative 1.29 divided by its standard error, which is 0.69. What is your answer? Negative 1.87, right? Okay. So exactly the next slide I showed you, okay, the t ratio for log n rho is negative 1.87. So in this case, we can compare it with our critical value at 5%, which is negative 1.65, all right? Because negative 1.87 is less than negative 1.75. Okay, basically it's in the rejection region. Okay, let me show you here. So basically it's in the rejection region, right? That's why we can reject H0. Which means the hypothesis that there's no effect of school size on student performance can be rejected because the hypothesis that there's no effect, which means our null hypothesis, okay? Beta log and rho equals 0. Can be rejected in favor of the hypothesis that the effect is negative. Next one, how large is the effect economically? Because basically, we do the hypothesis testing is statistically, okay? But how about economically, how large is the effect? So the coefficient is negative 1.29, right? Comes from delta math hat over delta log and rho, okay? So we're gonna use the approximation that delta log and rho is approximate to the percentage change of enrollment, right? And then we divide it by 100, which is 1 over 100 in the denominator. And then we get negative 0.0129, which is very small in terms of 1%. So in this case, we multiply 100. Okay, so you move the decimal point, okay? That's why you're gonna get negative 0.129, which means 10% enrollment increase, okay? Negative 0.129 percentage point student will pass the test, which means more enrollment, less chance for student to pass, okay? So statistically significant, yes, because we can reject the H0 and at 5%. But look at the size, which is 0.129 percentage point is very tiny. This is the key distinction for you guys, okay? Statistical significance is not the same as economic significance, okay? A result can be real, unlikely due to chance, but still too small to matter in practice. I think I'm gonna finish up here, all right? So what did I cover for today? Can you recall it for a little bit? Okay, please discuss with your friends. Please help me summarize what did I cover this morning. Please summarize and then we're gonna share your idea. So I'm gonna stop here. Next time, I'm gonna talk about testing against two-sided alternatives, okay? What did you learn? Let me